we move to the next speaker. Our next speaker is an associate lecturer, Mr. Yongtao Liu from Shanghai University, China. And his presentation title is Simulation Analysis of Regenerative Braking Control Strategy for Electrical Vehicles. Okay. Yongtao Liu is an instructor, I think is a lecturer of automotive service engineering at Shanghai University. He has presided over many provincial and ministerial projects and won many honors. Okay, without further ado, so Mr. Liu, can you give us the presentation?
Hello, everyone.
My name is also an online presentation.
And I come from Shanghai University, Xi'an, Shanxi Province. It's my great honor to make a presentation here. And the topic of my presentation is simulation analysis of regenerative braking control strategy for electric vehicles. This is the outline of my presentation. The first part is the research background. The second part is the related principles and modified model. The third part is control strategy and model construction. And the fourth part is simulation results and analysis. The last part is conclusions. Now for the first part, I would like to introduce the relevant research made by domestic and foreign scholars in this field. Due to the increasingly prominent environmental pollution, energy shortage, and other problems, solving the new energy vehicle technology with good energy conservation and emission reduction has gradually become a hot issue. However, the current development of vehicle batteries is not much, which leads to the short driving range of electric vehicles and hence the wider popularization of electric vehicles. Therefore, how to increase the driving range of pure electric vehicles through certain energy-saving technology is the key problem needed to be solved in the electric vehicle industry at present. So many scholars have carried out a lot of related research. The purpose is to improve energy recovery and energy efficiency. Based on the characteristics of the two gears electric vehicle, this study proposes a regenerative braking force distribution control strategy, considering the shifting strategy in the braking process, and carries out the simulation research. Finally, the energy recovery efficiency results of the two gears electric vehicle under the two braking control strategies are obtained. The second part is a detailed description of the relevant principles and the revised model. So what is regenerative braking? Regeneration is to achieve the regeneration of braking energy. Braking is to generate the motor braking torque in the process of power generation through the transmission system to the driving wheel braking effect. So the regenerative braking is a technology that can realize the regeneration of braking energy and the motor braking torque generated in the power generation process can produce braking effect on the driving wheel through the transmission system. Obviously, regenerative braking is a significant advantage of electric vehicles. In this study, regenerative braking torque was corrected by taking into account ECE braking regulations, battery state of charge, and motor peak torque. A detailed description of the modified model is as follows. In this study, the range of full braking force distribution coefficient of mini electric vehicle is from 0.72 to 0.86. When beta takes the maximum value of 0.86, the max regenerative braking force of the regenerative braking system of the front drive vehicle can be represented, and the max regenerative braking torque of the motor under the restrictions of ECE regulations can be obtained. Combined with the theoretical knowledge of the motor and the known parameters of this model, the max torque of the motor can be obtained. Considering the charging characteristics and the charging of lithium-ion battery, the regenerative braking torque generated by the actual motor was obtained. Then the speed impact fact and the battery impact fact were introduced to get the corrected max regenerative braking torque generated by the actual motor. The following part is the control strategy and the model construction of this study. Firstly, the right part is the parameters of the research selected in this study, and the left part is the vehicle model built through MATLAB and Simulink. Then the serial and parallel regenerative braking force distribution control strategies in this study are described. The front axle mechanical braking force, rear axle mechanical braking force, and the regenerative braking force on the different braking intensity levels. And the two strategies are listed respectively. The serial braking force distribution strategy firstly distributes the total demand braking force to the front and the rear axles according to beta is equal to 0.75. The parallel braking force distribution strategy adopts the combination of motor braking and mechanical braking. So the front axle mechanical braking force, rear axle mechanical braking force, and regenerative braking force are different. The safety strategies in this study are described as follows. When the vehicle braking speed is greater than 7.7 meters per second, The second gear is selected as the braking gear. The two theoretical regenerative braking force are compared to determine the max braking force and mini braking force, as well as the corresponding gear Kmax and the transmission ratio Imax under the max braking force. When the regenerative braking force required by the calculation output in the strategy model is less than the mini braking force, the actual regenerative braking force provided by the mode is the regenerative braking force required by the calculated output in the strategy model, and the gear is unchanged. When the regenerative braking force required by the calculation of output in the strategy model is less than the max braking force, the actual regenerative braking force provided by the mode is the regenerative braking force required by the calculation of output in the model, and the gear is switched to Kmax. So when the regenerative braking force required by the calculated output in the strategy model is greater than the max braking force, the actual regenerative braking force provided by the mode is the mass braking force, and the gear is switched to Kmax 2. The fourth part is the simulation results and analysis. The American Standard Urban Cycle Condition, UDDS, and the simulated braking condition are selected in this study to carry out the simulation respectively. For strategy 1, the serial regenerative braking force distribution control strategy combined with regenerative braking shift strategy. For the strategy 2, the parallel regenerative braking shift strategy combined with the regenerative braking shift strategy. After the simulation, the final SOC value of strategy 1 is 0.7095, and that of strategy 2 is 0.6736. The final SOC value of strategy 1 is 5.3% higher than that of strategy 2. So for the energy recovery, the energy recovery of strategy 1 is 20.8% more than that of strategy 2. With the participation of regenerative braking, the mode has effectively recovered the braking energy, and the regenerative braking recovery energy also shows an upward trend. For the simulated braking condition, as the braking strength is below 0.15 in the circulating condition, a middle higher strength braking condition of the 26th through the MATLAB and the Simulink platform is simulated and analyzed. After the simulation, the battery SOC value of strategy 1 is 0.7928. The battery SOC value of strategy 2 is 0.7922. Also, the energy recovery amount of strategy 1 is about 56% more than that of strategy 2. The pure electric vehicle with severe regenerative braking control strategy has a higher SOC of the battery and more battery recycling braking energy. The last part is the conclusions. For the 2-gear mini pure electric vehicle in this study, the energy recovery effect of the severe regenerative braking control strategy combined with the shifting strategy is obviously better than that of the parallel regenerative braking control strategy under the same working conditions. The severe regenerative braking control strategy combined with the shifting selection strategy is a feasible and effective method to improve the battery energy recovery of this model and extend the driving range of the electric vehicle. This study has good practical significance to improve the energy saving effect of similar electric vehicles. That's it. Many thanks for your attention.
Okay, thank you, Dr. Liu. Thank you for your excellent presentation. Since Dr. Liu is not available to answer questions, so we just move on to next speaker. Okay, he's not available to answer questions. Right.